Okay, we're now going to look at a average power problem. Um, so obviously you might expect that we have some complex impedances, and we indeed do here. So this is uh, really going to be done by me, at least as a complex power problem. It says calculate the average power generated by the J10 amp source. So that's this one over here. Well, for me, when I'm doing average power, I'm likely to always just do complex power. Um, I I do not know if these are in RMS or peak values. I actually sort of suspect that this is peak, and my formula here is for when V and I are in RMS. So we'll find out what happens. If it is in peak powers or peak amplitudes for the sources, then the formula I need to use is 1/2 VI conjugate. So this is the formula if they're in RMS, and typically it will say they're in RMS, and this is the value or the formula to use if V and I conjugate are in peak, or V and I are in peak. Um, okay, so we can see that we've got two current sources. I think probably the easiest thing to do, in my opinion, is just do a nice little uh, KVL equation. Call this, a KCL equation, use nodal analysis. Call this my reference node down here, and then call this voltage up here V1. Both of those are current sources, so this will work all nicely. I can say -10 plus V1 over 5 angle 50 degrees plus V1 over 8 angle minus 20 degrees. Now notice this 5 angle 50 degrees and 8 angle minus 20 degrees, if we actually calculate, for example, the 5 angle 50 degrees, we could say, well, that's 5 cosine of 50 plus 5 sine of 50 times j. So it is a complex number, and it basically contains a resistive component, and it contains a reactive component, so that we could combine those and say it has R plus JX. So that's not really a big deal, but it is something that uh, can take into account. By the fact that that angle is positive for the 5 angle 50, that tells us that it's actually partially inductive because of the plus J sign that we see here. For the 8 angle minus 20, that's going to cause us to have a negative reactance, so that would be a capacitive, because remember, impedances for inductors are J omega L, so you'd expect plus J's. Impedance for capacitance is minus J over omega C, so you would expect negative reactances there. Okay, so we got -10 plus V1 over 5 angle 50 plus V1 over 8 angle minus 20 minus J10 equals 0. So I'm going to solve for V1. V1, well, let me take terms out here. I'm going to have 1 over 5 angle 50 plus 1 over 8 angle minus 20 equals 10 plus J10. So my next step is just to solve for V1. It's equal to 10 plus J10 divided by 1 over 5 angle 50 plus 1 over 8 angle minus 20. Okay, so when I calculate this, let's see what we get. Okay, I'll keep my 10 plus J10 in the numerator, and in the denominator, I get that 1 over 5 angle 50 plus 1 over 8 angle minus 20 is 0.246 minus J 0.11. And so in polar form, that would have been 10 plus J10 over, not that this really matters, 0.269 angle, or actually 0.27, it's really close to 0.27, angle minus 24.2 degrees. Okay, so when I multiply or take 10 plus J10 divided by that, I will have looks like my V1 is 18.64 plus J 49.02. So that's my V1. So now I need to find what it's asking for. Okay, it's asking for the complex power, or the average power generated, excuse me. Okay, so I'm going to find first the complex power generated by the J10 amp source. Okay, so J10 amp source is doing this number. Alright, if I'm finding complex power absorbed, I know that I'm supposed to have the current flowing from plus to minus. Okay, so that voltage would be, if I call it Vs, you can see that Vs is the opposite of my V1, because V1 is plus to minus that way. So if my complex power absorbed is Vs, times that J10 conjugate, and again, remember, I need to say, because I think this is in peak values here, I need to say 1/2 Vs J10 conjugate. Well, okay, what's Vs? This is going to be 1/2 Vs is minus my V1, and J10 conjugate is minus J10. Okay, so I'll have the minus and minus will cancel, and I'll end up with 1/2 V1 times J10. Okay, and that is the complex power absorbed. So the complex power absorbed, when I multiply that through, is going to be, let's see, I have to take 0.5 for the half. V1 is this 18.64, and J 49.02, and it needs to be multiplied by J10. So I get that my complex power absorbed is minus 245.1 plus J 93.2. Okay, the last thing I have to do in terms of this, at least, is to say the complex power delivered is equal to minus the complex power absorbed, so that's equal to 245.1 minus J 93.2. Now this problem specifically asks for the average power. Okay, the average power is the real part, so it's P plus JQ. This is reactive power, this is average power. And now both of these would be average power delivered, reactive power delivered. So my average power delivered, so P average delivered, is equal to 245.1, and the units on that is watts. So does that agree with our answer up here? Yes, it does, and we are in good shape. So finally, I'll say the last thing is that these values given to us here were obviously in peak, so we had to use the 1/2 VI conjugate form when we calculated everything. Or if we would have gone ahead from the beginning, we could have divided the 10 amp source, we could have divided by square root of 2, and we could have divided the J10 amp source by square root of 2. Then everything would have been RMS, and then we could have used the VI conjugate formula for complex power, but of course you can see that that results in the same thing.